back. It's been a while, um, but yes, I'm ready to start testing this crap. This crap being Redstone comparison. So, key is to input a number into all this. Now it is ready to receive a number. Start with 1. See, it's got a 1 stored in it, all of those are off. And then it is inputting 1, so the output should be both of them off, which is correct. Now if I turn this off, it should turn the inside track on, so like that. And every single one of these should leave that on. When I'm done with all this, that number should be still that should still be the yep. Ooh. Now why is that not working? Oh, it is working, it's just not propagating far enough. Need to put this here. So obviously this is designed to take signal full strength there. But you know, if it's coming up the ladder, then it's not a full strength. So yes, that's working. Now, what you have to remember is that I'm not. There's no way I can comprehensively test this unit because there's so many possible numbers. So I've just got to try and come up with a good routine that I think will cover a lot of edge cases. The problem is I haven't really done that. Excuse me. So this is kind of just guesswork, and it's quite possible that there'll be some hidden errors that I don't pick up on in this system. And if there are, that will be extremely painful later. interesting potential flaw there. If I switch this off, that briefly turns on due to the lag in which system. That's quite odd. It would help if I could see better. Because there should not be any feedback up here. Just realised there's a redundant redstone bit there. Right, there shouldn't be a way for a signal to come back up here to the top from the next layer down. Which means that if turning that off is turning this on, it's because that's allowing signal to propagate under here somehow. So, you switch that off. Look at the top layer, for example. If I was to switch this off, would that turn that side off? Oh yeah, now I understand what's happening. Switching this off momentarily releases that, which allows this. Shouldn't be an issue. Did that correctly shift the system? Yes, it did. Okay. That does put me in mind of a failure mode I need to specifically verify. I think I don't need to test those. Obviously I'll be testing those when I get to them anyway. So I think I can just get away with doing that. Really, I have no idea what I'm doing with this testing in air quotes routine. Just sort of stumbling around, hoping that any error is manifest, and I figure out an efficient way of checking it as I go. Actually, I mean, we already caught one error, so... That was rather easy to fix, at least. Oh, yes, that's a mistake. No, this is a mistake. It's not meant to be like this, he insisted. Stanley kept on walking. I'm real, I'm a human! Hang on, what am I even doing? Yeah, right, that's what I'm doing. Why is that still on? Also, it's not particularly... Stanley Parable isn't a particularly obscure reference, is it? That's why it's on. That's why. Right, okay, so... I want to see if there's issues when there's coupled pairs of numbers. Coupled, but whatever, when they're next to each other. Contiguous. So that seems to be okay. We can go back into that state. So that seems to be at least functional. The question is, do I test this side in the same way that I tested that side? And what other tests can I do here? Right, this is... The bad news is I had a headache when I started today, so usually I only get one after I spent several, an hour or so building buses, but I had one going in, and this is quite dizzying. See, if I want to test the... Why don't I do this? Why don't I... So if I switch this on, that at least is correct. Now if I switch all of these off, still on. Should turn off. I suppose what I want to do is check the propagation, the down propagator on the inside track here. But have I already done that? Potential failure mode. This is it propagates backwards, but it doesn't propagate backwards anywhere. It couldn't propagate backwards. I was very rigorous in that design. If it propagates from top to bottom then. So I've already verified that it does propagate down everywhere. I have to be honest. I think I have tested it enough, which is unfortunate because I don't have anything else planned for this episode. I mean, I guess I could build up the edge here for the input bus. And now that I'm looking at this, this is going to be a bit tight with that. But I think I won't. I think it's a design decision. I want to get logical operators pretty much to this level of completeness, and then when I cut and paste them into the processing bus over there, I'll sort out the connectors. Now, there is the matter of the output from this, which is going to have to, in a rather ugly way, loop round here. I suppose what I could do is I could have a kind of ram's horn system where it loops under itself and out like that. That's an interesting idea. In fact, why don't I do that? The only thing is that would lead to the signals being inverted. As in, this is the first number to go in comes out on the inside here, and then it'll be coming out on the outside there. But I don't think that will be an issue. I think I'll just, something I can keep track of in my mind. Also, it doesn't really work with glass, does it? Because you can't step down on glass, which means that would ruin the aesthetic. Anyway, if you're wondering what I'm trying to do here, I need to get these signals out here. Which is obviously very easy to do, but the question is how to do it in a way that's aesthetic. And I was thinking I could build some kind of ram's horn, comes down and under. I guess this. But it's pretty ugly if it's made out of wool. It's certainly an ugly idea like that. Just go for the snail shell spiral. I need to think about that as well. I need to think about... I mean, I guess I don't, right? I don't care about propagation speed. Because this is all taking place. Signals will be propagating down this line whilst the CPU is in the process of cycling and loading the next instruction from memory. Which basically means it's got all the time in the world. There's no need for install as or anything like that. This can just passively feed forwards. I don't need to make the path short or anything. It's got about 4 seconds, or well, at least 2 seconds while the CPU is loading the next instruction. That way, if I extend it like that, well, I guess that does look a bit too much like a never mind. I was going to say it's going to make it look more symmetric and like a spiral, but can't be doing that on stream. It still does kind of look like a particular Hindu symbol, I'm afraid. But it has a utilitarian purpose, so. I might revisit that design. So basically needs to be like this. Right, so next stream, which will hopefully be on Friday, will be me building. We'll start work on binary multiplication. So that's going to be a complicated one. Now I've done my best not to contaminate my mind with like actual binary multiplication circuits. So I have a few ideas for how to do that. It's somewhat complicated. I'm by no means sure my ideas are optimal, but it seems like it's going to be quite a monstrous circuit. Um, like it's going to be enormous. In fact, I may as well start doing a bit of work for it now. I can copy and paste the foundation for it. Let's see. Excuse me. Right. I'll be building it that way so this is enough space. But when it's done, the actual circuit might be too big to fit in that gap. Oh, it's terracotta. Ugh, don't want terracotta, I want concrete. Is there any difference in the texture? Or it's, yes, there's a significant difference in fact. This is just going to be sort of the staging area for the binary multiplier. That's how big it's currently going to be in my current design. Right, so, first things I can probably actually leave that red bus in. I probably could have left that red bus in as well, because I may as well keep this memory circuit in the same spot, right? So I can probably keep the memory tower still here, address bus still there, put the switch there. So that much is probably going to be the same, which means I may as well actually copy and paste it over now. Although one part of this design I'm really going to have to consider is I'm going to need to put a lot of insta wires in. So what I might actually want to do is shift the memory circuit over to there, so that there's room for this outer line to be insta. Well, no, there's no need for insta wires on the ends because of the speed of the memory bus. It doesn't matter. So there's no need at all for that, because the limiting factor there is the memory bus, not the memory bus, the memory stack, memory registry, or whatever you'd call this. was that terracotta? I put in a piece of terracotta somewhere around here. Ah, there. Ew. That looks correct, yes. Excuse me. Ugh. I just need to remember to add those back on once I'm done. Excuse me. Right. Now the actual first bit of infrastructure I need to work on is a set of bit shifters. So I need to have a 16 element, a 16 bit shifter. Um, Also, because of the nature of overflow and multiplication, it's possible I can get away with them not. For example, I could have like, if it's the 16th bit, if the two numbers, if I know that the two numbers are, what's the smallest pair of numbers that will, 18, not 18, whatever, what's the smallest pair of numbers that when multiplied together is in the limit of 16 bits, for example. I could just make the system up to that size, but I think I won't because it's all parallel computing, so having it more doesn't slow it down, it just makes the circuit larger. Um, Now a bit shifter is very simple. Literally, it just involves rerouting the. It's just going to be a bus, and everything's going to get stepped up by however many bits it's being shifted by, right? So, alright, let's have a quick talk about. Well, my first idea, of course, is that binary multiplication is just sequential summing, right? So that's the binary adder over there. You could just run it through the binary adder however many times. So if it's 16 times 10 or whatever, you could you could add 10 to itself 16 times. Now, obviously, that's extremely slow. That's very slow. So we won't be doing that. What instead you do? Obviously, secondary adder is what obviously multiplication is. You take every tens term out, right, and you multiply a number by that power of 10. So if you've got 22, right, if you've got 22 times 40, you multiply by 40 by 20, and you multiply 40 by 2, and then you add two of those results together. To me, this feels like it's the most optimal way of doing it. And obviously, what that corresponds to is, in binary, what that corresponds to is if you're multiplying, obviously you bit shift by the power of 2. So let's say you've got 8 times 4, right? We're saying 8 is the multiplier, right? No, that's a distinction that matters in math, being commutative. But in terms of this computer circuit, it doesn't matter. So the multiplier. So you essentially bit shift you would be a bit in third position, right, for 4. So you would bit shift that by I guess 8 places. Is it 8 places or is it? 8 times 4 is 1632. So 32 is 2 to the power of 3, 4, 5. So 8 is in the 5th bit position. 4 is in the 3rd. And you need to bit shift it to the 6th. So yes, so you need to bit shift it by 2. But except you need to bit shift it by 3. How do you derive that law? I swear there's a very simple thing that I've forgotten because I am feeling a little confused right now, to be honest. This should be incredibly simple. 4 is in the 3rd. 4 is in the 3rd. You want it in the 6th. So you have to bit shift it by 3. But the question is, where do you get 3 from? Because 8 is in the 5th position. No, 4th position. say it's 16, so you've got 2 times, you've got 8 times 2. To get there, you need to bit shift 2 by 2 is in the so if we ignore 0 from God, I'm really 2 is in the second position because you've got 0, 1, 2, 3. And yes, 8 is in the 4th position, and 16 is in the 5th position, and yes, so if you bit shift, if you assume that 2 is in the 1st position, and then you bit shift 2 by 8, which if 2 is in the 1st position, 8 is in the 4th, 3rd position, then that puts 2 into the 4th position, which would be 16. That is a coherent law, potentially. So if you have 8 and 4 is 32, you have 8 is in the 3rd position, 4 is in the 2nd position. You bit shift 4 by you bit shift 4 by 3, which puts it in the 5th position, which puts it in 32. So I think what it is you have to remove the first bit, which is the power, which is 0, right? It's 0 or 1. I think you have to remove that from the thing, because obviously you multiply by 0, it goes to 0. If you multiply by 1, it's equal to itself. I think so. I think you bit shift it by the position of the multiplier bit minus 1. Let's say for the sake of argument that your multiplier is the largest possible number allowable in a 16-bit system, which I can't remember off the top of my head. It's like it's quite large. Well, it's like several thousand, like 10,000 or something. It's then you're going to have essentially 16-bit shifts of the non-multiplying number. Well, not numbers being multiplied, right? So you have it's going to get bit shifted into 16 separate numbers, and then you're going to have to use a binary adder to recombine those. But it's going to have to be a triangle of binary adders. And that's my current plan. Now, this is likely horrifically inefficient and not particularly good design, but that's sort of the point. The point is to sort of suffer through it. And because I'm quite confused right now, I think I shall log off, so thanks for watching. Quite confused. Let me know.